How can a system that just multiplies static numbers together, a network with no memory built in, actually remember the start of a paragraph by the time it reaches the end? Language is sequential. The grammar of the 10th word depends on a subject you established back at the first. To see how badly a basic network fails at this, there's a brutally simple test. The human numbers dataset, literally just the numbers 1 through 10,000, spelled out in English, one after another. Feed a plain network that sequence and ask it to predict the next word, and it fails spectacularly. Show it the last 3 words, and it might pick up a local pattern, but it has no idea where it actually is in the count. It's trapped in a 3-word window with no sense of the sequence as a whole. So how do you give a static web of weights an actual memory? You add a loop. Instead of pushing data straight through from input to output, you take the output of a hidden layer and feed it back into itself. That's a recurrent neural network, an RNNN, and its defining feature is something called a hidden state, a matrix of numbers held in memory, updated every single time the loop runs. Trace it. The network reads, word 1 computes and updates the hidden state. Then it reads word 2, not in isolation but combined with that hidden state, which now carries a mathematical echo of word 1. Multiply them together, update the state again, move to word 3. The hidden state acts like a rolling snowball of context, picking up a little more of what's been read with every step, carrying it forward through time. Sounds like the perfect fix. It creates a different kind of disaster. Remember backpropagation, tracing the error backward through the network to update every weight. In an RNN, every single loop depends on the one before it. Feed it a 10,000 word document and the loop runs 10,000 times, which means for the backward pass, you now effectively have a network 10,000 layers deep. The computer has to hold the gradient calculation for every one of those 10,000 layers in memory simultaneously just to take one learning step. GPU memory overflows, training crashes. The engineering workaround is called truncated backpropagation through time, truncated BPTT. It's a calculated compromise. The hidden state keeps rolling forward without interruption, so the network never actually loses its running context. But when it's time to calculate gradients and learn, the system artificially severs the computational graph every so often, say every 70 words, and simply refuses to trace the math any further back than that. The memory keeps flowing forward. The learning signal doesn't. That's how you give a machine something it was never built with, a working memory. And the compromise you're forced into the moment you try to actually teach it something from that memory.